All right, good morning, everyone. Let's start. Do you have any questions before we start? Okay, so we finished, right? So last time, we finished, I think, chapter 11, confidence intervals. So we will start chapter 12 this week, hypothesis testing. But before, so actually in connection with this, let's kind of revisit the confidence interval a little bit and ask the following questions. Is in relation to the two sample, the test of the difference of the two populations, right? So let's recall, we discussed this question. For example, if I have x1, let's do this, right? Why do we do x? Let's do x and y. x1 up to x n1, IID, normal u1 sigma 1 square. And let's do y1, yn2, IID, normal mu2, sigma 2 square. Okay. And so we said that, right, if, or assume, right, sigma 1 square equals to sigma 2 square, then the, 1 minus alpha confidence interval for mu1 minus mu2 would be, let's say x bar, right, minus y bar, and then plus minus t, right, t n1 plus n2 minus 2 alpha over 2, and then the pool, right, square root of 1 over n1 plus 1 over n2, etc., right? And all the details about the t confidence interval. So the question here is this assumption, right, which we kind of say, well, at that time we assume that, but if you are a good statistician, you should ask this question, that how do we know, or how, right, what is a reasonable way to check if the assumption sigma 1 square equals to sigma 2 square holds? How do we check that? What do you think? So you're having two populations, right, where all the parameters are known. You say that if the two population variances are the same, then you can go ahead and form this confidence interval. But, these are just random, right, samples. How do you know that what you say about the assumption holds or not? Or at least, right, you should kind of make sure that the assumption is not violated in kind of a very unreasonable way. Is there some way that we can go about checking this? So, all right, actually, right, with the knowledge you have had so far, there's at least several things you could do already about this question, right? So there's no right and there's no right or wrong about this kind of thing. It's really right because these are unknown parameters. So you just try your best, right, to give reasonable answers to these kind of questions. Well, first of all, right, you should kind of look at S1 squared and S2 squared. Because they are estimators for sigma 1 squared and sigma 2 squared. Now, suppose that even if that is true, that sigma 1 squared equals sigma 2 squared, is it going to be true that S1 squared equal to is it going to be true that S1 squared is equal to S2 squared? Even if, right, even if our assumption is true, would that be the case that necessarily S1 squared equals to S2 squared? Okay, yeah, depends on n is a reasonable thing to say, but right, and here the two sample sizes are different, but that's fine. But even if n is large, right, even if n is large, will S1 squared will be equal to S2 squared exactly? Not quite, right? Because S1 squared and S2 squared are always random variables. So even if these are the same, they are not going to be equal. Okay. So the most reasonable thing for you to say is if they're approximately the same, right? If they're approximately the same, then you would say that, well, then it's reasonable to say that the assumption holds. But the statement that these guys are approximately the same are quite vague, because how approximately the same are approximately the same, right? Is 1,000 approximately the same as 1,005? Is 1 approximately the same as 2? Okay, so many right, vague things are left at the statements. So of course the idea is something around this line. In other words, to see if the assumption holds, you check the estimators. And by the way, right, this is exactly one of the places where you use the estimators to give you information about something that you don't know. So you want to check something like this, except that because they're random variables, it's never going to hold exactly. But approximating, right? Approximation is a very vague statement. So you want to make that more precise. So how to make that more precise? Well, one way is through the notion of the confidence interval that we have done so far. So what you would do is you would, so more, right, how to say this more precisely, we could form the 1 minus A1 minus confidence interval for sigma 1 square over sigma 2 square. Okay, and we know how to form this. That's actually exactly the one of the chapter, right? Forming the confidence interval for the ratio. Now, this being a confidence interval, right? It will be something like something left, something right. So if I remember correctly, I hope I'm right. Well, it should be something like this, right? S1 square over S2 square, and that will be an F, right? It will be an F. It will be an F distribution. So if I remember correctly, it's something like Fn1, N2, and which one is bigger? the 1 minus alpha is the smaller one, and then okay. So let me check real quick to make sure that I'm right on this. I think I'm right. I always have to go through a derivation to write down, but oh, there's a 1 minus, right? There's a -1 ratio. And then this is alpha over 2 actually, and this will be 1 minus alpha over 2. Yeah. I mean, I'm not trying to form it exactly, so I am, but I'm a little confused. Between these two numbers, this one is bigger. Oh yeah, so it's small. Fine. All right. So I'm not trying to form the confidence interval here. So, but this is the right one. Okay. But then the question is, right? What are we gonna check with this confidence interval? These are just numbers in practice, right? These are just numbers in practice. So to be concrete, let's suppose that you get something like 1.2 and 3.8, for example. So let me ask you this. Suppose that, right? So again, what's the question? The question is, we have two samples. We want to really form for the confidence interval for the difference in means. Okay, but to do that, you need to check this assumption. Otherwise, this form. Oh, it's actually easy, right? It's a trick. These two numbers, which one's supposed to be smaller? Which one is a smaller number? No, I mean like what? Number as in like this whole thing. The left number is supposed to be smaller, right? I mean, because it's a left number. But if it's a left number is smaller, then this must be bigger because it's 1 over ratio. But in terms of the quantile, right? In terms of the quantile, alpha over 2, I mean, of course, we always think of alpha as small, right? Conventionally, we don't think of alpha as large. Then definitely alpha over 2 is the one. No, it's fine. I got that wrong too. So don't worry about that. But that's where you need to know how to check it, right? Making an error is fine. Just understanding the concept to be able to check it. Okay, like I did. Anyway, the point being is, again, I'm not interested in confidence interval now, right? We're done with that. What I'm interested in is how you understand the confidence interval. So in other words, to check this assumption, now I form the confidence interval for the ratio. It's some abstract formula, and we explain why the abstract formula is that way. But now, suppose this is the concrete answer. How would you use this answer to go back to the assumption? So if this is the confidence interval, what would you say about the assumption? Does it hold or not? If this is the confidence interval for the ratio, does the assumption hold or not? Right, and why not, Alice? Not include what? Not 0 here. You're right, you're thinking about the right thing, but it's not 0, right? It's not including what? Because actually, I can tell you this, the confidence interval here should never include 0. No. You're just thinking a wrong number, not including one. We're looking at ratio here. We're not looking at the difference. Yep. Okay. But you're right, right? You're looking for that magic number, which is one here, not zero, right? So the ratio here, if they were equal, it would be one. Now, so what we're saying is with some really large probability, like 95%, this, right, the real ratio is in this interval. And this interval, it does not include one. So with 95%, you are sure to say that the ratio, right, is not one. Therefore, your assumption does not hold. Is that okay? So here, this will you can confidently say with 1 minus alpha confidence level that sigma 1 square is not equal to sigma 2 square, right? And if the confidence interval is something like this, then you can say, yeah, at least the assumption that sigma 1 square equals to sigma 2 square is not blatantly violated. Is that okay? Now, notice the wishy-washy nature of these kind of things. This actually gives you a much stronger reason to reject your assumption that sigma 1 square equals to sigma 2 square. Here, right, actually, you never know. Here, it could be really that sigma 1 square over sigma 2 square is 1.1, which is inside this confidence interval, right? Which actually is not this assumption. But even if this were true, and this is the case, which lead to this case, we still cannot, right? Or we still say that this is acceptable because with all the evidence we have and with all the technology we have so far, this is the best we can conclude. Okay. Any questions so far? So I'm bringing up this example because actually a lot of this discussion you see is exactly hypothesis testing. Okay, we are testing the hypothesis that sigma 1 square equal to sigma 2 square, but the approach. Oh, right here, Madaf, right here, right here, right here. The reason is right here. The reason is you see that things in life are random, right? So even if you think about the two sigmas can be slightly different, like this 1.1, or if you even want to be like more pragmatic, you can do 1.05 or something. If they are different by even a small number, then mathematically or whatever, right, pedantically we say they're not equal. On the other hand, because they're so close together, the confidence interval they generate, the confidence interval for the ratio can still cover one, right? And in fact, it is very likely to cover one. Okay. And there is a reason why we strongly reject here and we cannot reject here. The assumption that sigma 1 square equals sigma 2 square. It has to do with the convention and the way we approach hypothesis testing. Okay, so I'm using the example which is utilizing, you can see only the toolbox that we have done so far in confidence interval to show you, okay, the next chapter. But also this example is meant to tell you that hypothesis testing is an issue is a topic in of itself, because there are philosophical questions or conventions or things, considerations that are peculiar to hypothesis testing that we need to pay attention to. Okay, But yeah, one of the questions that you may ask Madhav is something like this. But here's just a concrete example to show you that it can happen. The more appropriate question is, why do we allow this kind of thing to happen? Or why do we set up our answer such that this is still acceptable and we don't reject it? That's more an appropriate question. But yeah, I mean, like mathematically, this can happen. Is that okay? Yeah. So again, so the point of me giving you this example, okay, are twofold. First of all, try to see the connection between all the things we've done so far. The whole point of statistics is to test assumptions in some way, actually, okay? Is to test assumption, to test things, to give information about things that we don't see. So even within, right, statistics itself, it may make assumption and then move on to do something else. But you can use the tools of statistics to test your own assumption, like this, okay? But then, of course, right, to be clear about what we mean, what we say, what we do when we talk about this, right, testing assumption, hypothesis testing is the rigorous way to do so. All right. So, okay. So 12.1, introduction. So as again, you know, I will follow the book somewhat, but I might pull topics here and there from different sections, not necessarily stay within the same flow as the book. But anyway, so first we just, I just want to give you a overall idea of what hypothesis testing is about. So first, the setup. The setup is the usual setup of statistics, that we have some kind of population and we have some sample from that population. So IID, and we can have two samples too, okay? But let's just look at one sample for now. IID from some population. Whose distribution, right? With distribution, with known distribution. Depending on theta. Notice that actually this is always the setup of this class. This is always this kind of thing. So, and again, the reason is because our class is really parametric stat, right? In non-parametric stat or in more advanced courses, the assumption of the distribution is also something that you put to the test. You don't assume that, you don't say that the distribution is known. But right now we say that we know it's normal, we know it's exponential, etc. We just look at the parameter. But anyway, the setup of hypothesis testing is we're going to have two hypotheses. One is called a null. One is called the alternative. Okay, and what are they? They are at the bottom of them, at the bottom of things. They're just statements about data, about the unknown parameters. They're just statements about data. So, for example, you can have x1, xn, IID, normal mu sigma square. And to make things easy, you can assume sigma square known. Again, you know, this is the pedantic device that we always do at the beginning of some concept to make things easy. So the hypothesis that we can have is the following. mu equal to 0, mu not equal to 0. That, you know, is like a classic somehow setup that you get introduced to when you look at hypothesis testing. But we can also have the following. Okay. So all four of these are all hypothesis tests. They all have the same null hypothesis, and they have different alternatives. Okay. Now, so what are we to do? Our goal in a hypothesis test is always to come up with a criterion to accept or reject the null hypothesis. Okay. So the context of hypothesis testing is you're given a random sample with some unknown parameters. Could be two, right? Could be both unknown, but unknown parameters. And you're given the statements that, let's say, you know, your client, your customers are interested in knowing, and it could be one of these statements. Your job is to come up with a criterion. So understand, okay, that all of these are kind of the understanding here is that you do this prior to seeing what the samples are. Okay, so all these are treated as random variables. So you want to come up with a criterion so that you say, okay, you know, customer A, look at this about your sample, right? For example, I mean, let's say you say that, I don't know, let's pick this test, okay? That's test number 1. For example, for test number 1, you can say you reject the null hypothesis if your sample average is bigger than 10. That's a possible answer. I'm not going to say this is the best or the worst answer. It's a possible answer. Okay. So what I'm trying to demonstrate here is this is what your client is looking for when they ask you this hypothesis test. That give them a criterion. And of course, here is implicitly understood that the criterion must be based on a sample, right? And it's based on a sample implicitly through some estimator, through some statistic. So come up with a criterion to accept or reject the null. So here you say that, right? Customer A, look at your sample. If your sample mean is bigger than 10, you can just reject the null hypothesis. Okay. Now, of course, there are a lot of things to go with, you know, the problematics that would happen when you accept or reject the null based on some criterion. Well, that's what we'll get into soon. For now, let's just kind of make some technical remarks on some of these hypotheses that may come up that, you know, people may question, may be confused about. But first of all, let me ask, is there any question about any of these concepts so far? Okay. So some remarks, they are not super important remarks, but they may come up. Yeah, absolutely. So the null hypothesis, remember, right? And one of the confusing thing about hypothesis testing, I think, not about the technical details, but more about the whole context, is they can be anything, right? Hypothesis testing can be like this. Mu equals to pi mu equal to square root 2. It is a hypothesis test. Okay. Now, of course, you will not see this on like an exam or on a typical example, but conceptually they can happen. So in the conceptual, abstract conceptual stuff, there's no restriction, and that's actually one of my remarks coming up. Okay, they are just statements. Yeah, that's another statement I will make. Exactly. Now that's another remark I will make. Yeah, I will make those statements. Exactly. These are the things that can be confusing. Exactly. Yeah, you guys ask exactly the question that will make the remark. So, so first, right, let's say exactly the remark of Derek, that there's no, in the abstract, okay, in the abstract, meaning no, without any context, there is no obvious candidate for H0 and H1. In other words, this is my answer to Derek, that it literally can be anything. Of course, you know, you with the context, then you can tell better. But so it really depends on context. Okay, this depends on context. Okay, for example, I mean the okay, we'll get there soon. But what I want to say is this. So in particular, the statement in the no, oh sorry, the statement in the alternative is not necessarily the complement of the no. Okay, I'm not sure if this is like what someone intuitively think about, or but I think most people tend to think that, right? And actually this goes to Madhav kind of question too in some way, that if you reject the no, then you have to say that the alternative is mu not equal to 0 or something like that. Okay, because right here, if you in this setup, if you reject the no, then the alternative is mu equals to 1, not that mu is not equal to 0. Okay, so the way one set up the no and the alternative has a lot to do with how one choose the criteria. Does that make sense? So just do not get into that the rigid framework that if I do this, then if I reject this, then I will go to the complement. That's a logical statement that does not have to hold in hypothesis testing. In hypothesis testing, H0 and H1 go together. You have to look at both and then see your criteria. Okay, so in that way, it's just context driven. It really is about your client. Okay, your client likes this. Your client likes this. You know, and they want to set up the question, the test that way. But then, right, even with after you set up the hypothesis, now that goes to Madhav's question. Conventionally, reject H0 is the same as accepting H1. All right. By this, I guess I mean me, meaning in my class, I don't care if you say one or the other, or actually at the beginning, okay, don't worry too much about these distinctions. Rejecting the one, it means accept the other, all right? But let me tell you that in practice, people do split hairs about this kind of thing. In practice, and in fact, right, the next chapter, you will see that rejecting one does not have to. So this is my class, okay? Let me just make it clear. This is not even, you know, the statistician convention. This is my convention, meaning I don't care, because we're not pushing the boundary here. We're not doing real experiments. So, I just want to show you the concept, and I'm more math driven. But in practice, rejecting, right? Let me say this. Actually, is this not rejecting the no may not imply that you accept the no. Okay, because people prefer to have this kind of gray area where they say judgment suspended, suspend judgment, meaning you don't want to say much about this. Okay, so in other words, like, I'll tell you why. Okay, again, it's experiment driven and it's about like human way of looking at things. So as you can see that because this gray area is really, not something that we need to add on top of our technical details. So for me, it's much easier for me to go with you guys and say, okay, rejecting one is accepting the other. All right, just for our class. But do just keep in mind, exactly in Madhav's question, there are gray areas where people say, not rejecting one doesn't mean you accept the other. So in fact, the most common statements I have seen, okay, in hypothesis testing in practice, and this might be a little bit loose because I've only seen practice quote in academic setup, is people like to do reject the no or not. These are the statements I see the most. Reject the no or not reject the no. That's what I see the most. So this may be the safest thing that people tend to say. All right. And you may see that I am in the habit of doing so too. But like, if you want to interpret any of these in other ways, feel free. Just take my warning that you want to be aware of how other people approach these kind of statements, okay? And don't be hasty to go to the statement that people may frown upon because they don't think that's conventionally the way. Right? I'm not here to teach you this exactly because I'm not super aware of like the context, but this is the one that we'll go with. Okay. Any other question about this? Before we move on and make some more remarks. Okay. So the next remark is actually go back to number one. How is the context driven, right? How does the context drive the no and the alternative? So there, like I said, there usually is no rhyme or reason to put the no and the alternative. At least when you start out learning hypothesis testing, you can just literally throw anything at it and just test your understanding of technical concept. But in reality, okay, in practice, I can tell you this. In practice, or in a lot of, and by practice here, I do mean like, just academic practice too. It doesn't have to be like out there practice. The alternative are, so the no hypothesis is usually the default assumption. Now I know that doesn't help too much. What does default mean, right? So default really depends on context. We work in that environment so much, you know what default means. Default assumption, I will put something more, no information assumption. safe assumption. Okay, I'll give you an example to demonstrate this. H1 is usually the interesting assumption. The one that gives you information, okay, the one with info. Now, again, keep in mind that, right, these language are very loose. Okay, this is my way of interpreting things. It's not really, you know, anyone having a rigorous definition of what these are. But let me give you example. Example are plenty. So, for example, in a treatment, okay, and you can think of, like, you know, right now, COVID-19 vaccine, okay. In testing any kind of treatment, okay, any procedure, the null, you can pretty much be 99% sure that the null is treatment has no effect. And the alternative is treatment has some effect. There you go. That's it, right? And so you see, that's what I mean by default assumption. No info assumption and safe assumption. It's always safe to assume the treatment has no effect rather than having some effect. So I will be very surprised if somehow this guy gets swapped. All right, so that's how it is. And you know, because, right, effect is usually coded by the level. So that's why usually it's get translated to mu equal to 0 and mu, let's say, positive, or mu not equal to 0. Because if you measure your treatment, your treatment by, let's say, I don't know, difference in blood pressure, blah, 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 you see no effect usually somehow get attached to the number 0. It got kind of like calibrated to 0. And that's why you usually see this. But you see, right, no effect doesn't have to be at 0. It could be at 1, like with our comparison of the variances, right? So this is purely artificial. It depends on what context you read at, right? So sometimes no effect may be a 1, for example, who knows? But so from here to translate to the math is another step, but that's usually the case. In terms of, like, let's say, you know, let's say, I don't know, like a court, right, criminal justice, then the law, as far as I can tell, right, in our criminal justice system, is that the defendant, right, is innocent, and the alternative is defendant's guilty. Now, of course, right, I mean, this is, you see, purely convention. This is our way of thinking about things. I mean, there are some other places in the world, maybe that, you know, your default assumption is you're guilty, but who knows? But, right, so here is the safe assumption. And again, you see, safe depends on context. The last one is probably the something that you guys have seen before, regression analysis. So you would regress something like, you say y is alpha plus beta x plus epsilon, like this, okay? Where alpha and beta are the regression coefficient. Your null hypothesis is on the beta, and usually it's always that beta equal to 0. Why? Because if beta is equal to 0, that means y has no dependence on x. That's a no information assumption. And if beta is not equal to 0, then y has some dependency on x. Okay? And so these are examples that show you, right, why things tend to be set up this way. But, you know, in the abstract, you can put anything you want. And again, right, the alternative does not have to be the complement of the null, even in these kind of things. Okay. Any question? All right. So next, let's talk about a concept. This one is the rigorous concept. It's called the critical region. Rejection region. Okay. So actually, this concept is always connected with another concept called the test statistic. All right. So now what is a test statistic? What is a test stat? A test stat is a stat, right? A statistic that's used for testing, period. So, I mean, that one has no much information, but a test stat, I guess so. But if you want to elaborate on it, right? A test stat is a stat. By the way, right? This is where, again, you know, on day one, I told you a stat, a statistic is just something that depends on the sample. So it's something that you pull from a sample that tells us, right? That helps us to decide whether to reject the no or not. Okay. So in the business of, you know, remember at one point I said the goal, right? The goal is to come up with a criterion to accept or reject the no. So to come up with that criterion, your first task is to come up with a test stat. It's just the same as when you construct a confidence interval. Your task is to come up with a pivot stat, right? So here you come up with a test stat. And so you can see that the test stat here, right, is actually the absolute value of the sample mean. So this is a test stat in this example. So in general, you have some test stat that you want to construct. Okay, but a test stat alone is not a criteria, right? So then you need to say with, right? Then you need to say if, right, the test stat, let's say, and let us denote, right? Let's just denote it by, let's say denoted by, let's say theta hat. Okay, I mean, because the abstract parameter when we test is theta, so let's call it theta hat. But you know, theta hat here doesn't have to be the estimator of theta. Okay, I just call it theta hat. I'm not sure I should call it T or something. Maybe I should call it T, maybe, just to make it easier. Not confuse you with estimator. Okay, T for test. So if, right, the test stat well is in some region, and this region is you decide this, then you reject. Then exactly this whole thing is called the rejection critical region, and it's denoted by C. Okay. So for example, your critical region could be something like X bar bigger than 10. That's a concrete critical region. Another, suppose that you're dealing with the sample variance, it could be S squared is less than 2. Now, this is usually the ones you will see, but be mindful that, you know, again, in the abstract, there's nothing that says your critical region must have some shape or some structure. So in other words, your critical region, you know, this will be super weird, but it could be 2 less than X bar less than 3, union with X bar bigger than 100. Again, I'm not trying to say that this will happen in practice. All right, things like this will happen much more often. But for the discussion of concepts, don't limit yourself to something like this only, but having like, critical region is just something related to X bar, right? It to test that. It says that if the test stat is in some region, then I reject. You choose whatever region it is. So here the region can be that this is less than 10, bigger than 10. This is another one, right? And this is something else that we'll do with sigma squared. But anyway, this is to make the idea of the criterion to reject the null hypothesis more concrete. Okay, like this. Any questions so far? All right, so to summarize our goal, right, now that we introduced that language, our goal in a hypothesis test is to come up with a critical region or rejection region. I don't know. Sometimes I use the language rejection, which sometimes use the language critical region. That satisfies, right, some criteria. All right. So again, right, a hypothesis test has the null, has the alternative. Our goal is to come up with, a reasonable way to accept or reject the null, and that is coded in the critical region. The critical region itself, right, has some properties. And so now it's our job to understand, when you come up with a critical region, what properties can a critical region have? And by the way, behind a critical region, there's always some test stat. Okay, there's some test statistic. And again, the test stat is not something exotic. It will be related to the estimator in some way. But for now, in the abstract, let's call it test stat. So test statistic, critical region, hypothesis, right? Null hypothesis, they're all connected, and try to make that link in your mind, right? In a way, okay? So right now, so the next step is to understand what properties can a critical region have, and how does that affect the way we want to construct or shape our critical region. All right, questions? All right, so now the next one is the concept of errors, right? Errors that can be committed. In hypothesis tests. Okay. Now, you see that in hypothesis tests, right, you will accept, or in some way you will accept or reject the null. So there are two ways you can commit error, and they are very, I guess, creatively named. They're named type 1 and type 2 error. And I think you have, seen them before. So type 1 error happens when you reject the null hypothesis, but the null is true. And by the way, right, this right here is behind the scene, like peeking behind the scene. Of course, in reality, we don't know. But this is suppose that the null is true, meaning suppose that, let's say, the true mean is really 0. But somehow we go with the alternative, then we make an error, right? The type 2, of course, is the opposite. sorry, well, not reject, right? But we accept the no. But the alternative is true. Okay. So these are two types of error we can commit. Any question on this? Now, first, right, let's actually go back to the critical region and say one thing about them that is quite important. I mean, is quite obvious, but it should be emphasized that the critical region is a random region. Or a random interval in some way, right? In other words, the probability that you are in the critical region, right? That the critical region is for you are in it. So to be in a critical region means to have this to be fulfilled, okay? To be in a critical region means to have this to be true, for example. So what I'm trying to say is this, right? To accept or reject the no, you see if your critical region is fulfilled or not, right? To see if you are in a critical region or not. So let's look at the chain of decision, right? So you have H0 and H1. Okay, you have your sample, you have H0 and H1. Then you construct your test stat. And then your critical region. And then you try to see if are we in C or not. Okay, and so your test stat and your critical region are constructed in the abstract, all right? Like independent of what you don't see. So you construct your test stat and you construct your critical region, and then you look at your sample. You look at your actual sample, right? This is look at actual sample. And see if you are in the critical region or not. And then, of course, then you will reject or accept the no, right? But what I'm trying to say is, at this step right here, the fact that you are not in the critical region is a random event. Okay, it's a random event. By the way, so this is fixed and this is fixed. All right, fixed in the sense that you cannot change that number 10, for example. Once you say that you rejected this is bigger than 10, you're not going to say, I'm going to go back and change something, right? But so this critical region is fixed in a way. But because your sample is changing, every time you have a new sample, right, you have a chance of being in the critical region or not. So the fact that you commit type 1 or type 2 error is a random chance. Okay, so that's why we talk about the probability of commit type 1 error. And you talk about the probability of commit type 2 error. Is that okay? So that's actually the first thing that is kind of important about hypothesis tests. You will make error, but the fact that you make error, we can only talk about the probability of you making an error. Okay, that's all we can say. So same as when we look at the test, we look at the assumption on the variances, right? We say where was it? Right here. We say that we reject, right, the assumption that sigma 1 equals sigma 2. We could make an error here. All right, they could be in fact be equal, but we reject. So, but you see that in these kind of things, right, in this kind of decision, we always make an error with a probability. So here we say that with 1 minus alpha probability, this is not likely to happen. So we are confident up to 1 minus alpha. But so the fact is, right, error being made in this kind of decision are always random, right? There's a probability of you making an error. So the probability of making error, right, type 1 error, so will be coded as probability of C happens condition on the null. And of course, this is type 2, meaning you accept the null. So I would say C complement condition on H1. Is that okay? And again, they're given very imaginative names, alpha and beta. So these are universal symbols, okay? Most every textbook, you see this kind of name, this kind of ways of discussing things. So you should memorize and remember this. Any question? All right. So notice also here, right? There's something implicit here that I'm talking about, that the critical region is a region where you used to reject the null. So it also goes with the convention that if you are outside the critical region, right? If you are in C complement, then you go with the null, or you at least you don't reject the null. Okay, that's the conclusion, and that's up to you to say how you want to phrase that language. But as far as we're concerned, C complement is the opposite of rejecting null, whatever that means. Okay. All right. So now we can rephrase our goal of hypothesis testing one more time. The goal of hypothesis testing is to come up with C to minimize alpha and beta, right? So that, at least right now, that seems to be a reasonable goal to have, because these are two possible errors we can commit depending on whether this one plays out, that one plays out. We do not know which one will play out in practice. So we're just going to say that, you know, we try to construct a critical region that would somehow make both of these really small. Any question on this? All right. So now the next thing to observe, and then you might have seen this already, is that actually, right, this is not possible. In other words, you cannot minimize both of these at the same time. Okay. In fact, they tend to move in the opposite direction, right? In fact, right, and this is not a rigorous statement, this part, in fact, alpha and beta tend to move in opposite directions. Okay, but so let's see why. Let's see why. Let's show why this is not possible. Okay, so what would I do? Suppose I want to make alpha really small. What can I do? What can I do to make alpha really small? So you don't get to control that, okay, Madhav? So again, that is hard in the sense that you need to know what you can control, what you cannot control. I'm not sure what you mean by that, but if you mean like the problem, the null happen, that you cannot control. And by the way, the null either happens or not, right? That's not a probabilistic event. By the way, yeah, let's be clear. For example, There's no such thing. Because what is this? Mu is a constant. It's either equal to 0 or not. All right. In our setup, which is actually the frequentist setup, yeah, right. There is the Bayesian framework where you think of the parameters as a random variable, but we do not look at that. Okay. Here, so there's no such probability. So that's not what you're looking at. What can you control, or what actually what are you asked to control here? The critical region, exactly, Alice, but not making it larger, because I want to make alpha small. That's fine, right? And then exactly here, that's where you have to pay attention. But yeah, exactly, right? Make C as small as possible. And what is the smallest region you can come up with to make it to the extreme? 0, but here because a region, you know what? Empty. What do I mean by that? By the way, what do I mean by that in English? If I make C to be empty, what does that mean? No. Again, right? This is where you have to connect the language and the concept. What does C mean? C is where I reject the no, right? If I am in C, then direction is reject the no. But if I say C is empty, what am I saying? No, Derek. C is empty does not mean the alternative is true. Again, right? I do not know if the H0, H0, S1 are true or not. Okay. You're almost there, but yeah, Madaf is the closest. That means I never reject the no. Okay. So Christine is almost there, if that's what you mean. But pay attention. By this statement, this is my criterion. All right. I am not making any statement on the no or the or the alternative. Like I don't know. Okay. This is just my way of saying that the way I conduct this test is that I never reject the no. It's almost like, you know, a pharmaceutical company that says no treatment is effective. They can do that, right? They're crazy, but right. Or a judge who says everyone is innocent. Sure, right? He acquits everyone. That's his way of doing things, right? So when I do this, that means I never reject the no, right? Notice, right? For example, a judge who acquits everyone, that does not mean everyone is innocent, right? That's the reality. I don't know, but a judge has everything in his power to say that, you know, he acquits everyone. He thinks everyone is innocent. Is that okay? So that's what this is doing. Now, and you see, right, because you never reject the no, what's the chance of you reject the no incorrectly when it's true? Again, right, make things too concrete. If a judge acquits everyone, right, what's the chance that he will send someone to prison if that one's innocent? Is that clear? But then what is beta in this case? If a judge, right, acquits everyone, then if someone is guilty, exactly, not even not 0, 100%, exactly like what Christine and Maraf say. Okay. So when you try to make alpha as small as possible, you end up making beta as large as possible. And of course, you see the opposite also happens, right? You just have to just have to flip the thing. So now, right? I mean, like if you want to kind of demonstrate this statement, then exactly you just do the same thing, right? If you want to make alpha small, basically you just make C small in size, but that means you make C complement large. That means you make beta large. And again, right, these are heuristic statement because it has to how to play out this. Are you okay with this? Again, right, the whole point of this kind of thought experiment, or rather language experiment, is for you to work out this concept in your mind and be able to speak about it. I found that a lot of times the challenge is where you cannot connect the concept to the piece, right? Sometimes you think the no, and you say the no, you think the complement, you say critical region, you think that one. Anyway, right? The concept is a little more hard to keep straight. But if you keep it straight, then I hope it's fine. So for example, like this. The formal definition of C is just some region where if I'm inside that region, then I reject the no. C is your choice. C is your control. So that's why there's nothing to say about C unless we have a concrete example. But right now, right, C is anything that if it happens, if you are inside C, then you reject the no. Is that okay? For example, let me make a very silly example, but a judge, if he said that if everyone wears black, I mean, wears, dark suit, then he will say that person's guilty. Well, that's his critical region, So that's one way. All right. But but that silly example shows you that that can be anything really. It's just some region that if that happens, then the no is rejected. And you are the one who, when you conduct this test, you are charged to come up with your own critical region. Is that okay? Right here? Oh, okay, fine. So the no, when I say the judge, right, the no is always the person's innocent, defendant's innocent, person is guilty. By the way, this might happen in real life, God bless us, but who knows, right? But like this is it. And you can see that another judge can have another critical region, right? We hope that they don't play around with this kind of thing, but who knows? That's the thing. Is that okay? But the point is this: that this is the job of the judge, or the jury, right? I should say the jury, right? The jury does this, right? They come up with a critical region, isn't it? Yeah. And so, right? I mean, you can see that here, C can be empty. In other words, a jury person who says, everyone is innocent to me, I will not convict anyone. And it can be also, this is the universe, meaning a suspicious jury who says, right, that, juror who says that, everyone's guilty in her eyes. Okay. But it's really their construction, your construction. Question. All right. So then, right, the point of this discussion is that we cannot minimize alpha and beta at the same time. Okay, we cannot minimize alpha and beta at the same time. So in practice then, right, so the task, right, so the next goal is this, which is the final goal, which is the convention of hypothesis testing, is we will fix a level of alpha. And this is, of course, right, famously known as a significance level, right? Let's say 0.1, 0.05, 0.01, etc. And you come up with a critical region with, right? Oh, by the way, this right here, this quantity is also referred to as size of the critical region or size of the test. Okay, it's just alpha, but this is called size of the critical region, the size of the test. It's just a probability under a norm. So come up with a critical region with size alpha and beta as small as possible. Okay. So actually, this can be kind of, simplified in this, that's fix alpha, minimize beta. So in other words, right, because you cannot minimize both at the same time, you say that I'll give priority to one. I will make sure that one of them does not go beyond some level, some tolerance level, some significance level. And that significance level is alpha. Okay, like preset like 0.1, 0.05, 0.1. And while making sure that your type 1 error, right, does not go beyond that, you will choose a critical region that will minimize type 2 error. Is that okay? And by the way, right, I don't know, conventionally, this minimization is not spectacular. Again, why? Because you want to make this quite small. So in that sense, this is not too small. So usually I think beta is around 40%. The size is supposed to be less than this level. So this level are given. So let's say I give you, okay, and then you're supposed to come up with a critical region such that probability of this is less than or equal to 0.05, and then this is as small as possible. Is that okay? But in reality, you will see that because you want to make this as small as possible, you will make this C complement as small as possible. In other words, you want to make C as large as possible. So in reality, because this will always be equal, because you don't want to waste any, room that you have to move to make beta small. But this is a statement. Is this okay? What's the confusion about? Yeah, so, okay. It is alpha, and also the alpha is used as a notational level. Because trust me, it is a little confusing, but it is used in the same way. And you see why. Because this level is exactly this too. Yeah, that was alpha. I did not use it any other way. Fix a level of alpha. You understand alpha can change, right? But now I want alpha to be no more than 0.05. That's all. All right. So yeah, so I'm not sure I was in the middle of saying that alpha, when the alpha is around this level, beta is around 40% or so. So it's not spectacular, but that's the best you can do. And the philosophy of the test is like this, okay? And we will continue with this next time. All right, so if you have any questions, I'll answer them. If not, then I'll see you on Friday. Thank you. You too. Thank you. The exam will be up to this Friday's material. I'll tell you after I'm done with Friday, like what is it up to. It should cover some hypothesis testing. I don't know up to what.